Welcome to this screencast. This screencast shows how I model a cyber-physical system with Uppaal. Uppaal is an integrated tool environment for modeling, validation and verification of real-time systems, and it models those real-time systems as networks of timed automata. On the left side you see the URL where you can download Uppaal. As a disclaimer, I'm not an expert in Uppaal, I just started working with it. But maybe this tutorial is still interesting to you because you're also a beginner and you want to see how you can use this tool in your work. And I also tell you about which difficulties I noticed when working with the tool. What we'll model as cyber-physical system today is a temperature-dependent resistor. So basically we want to model a thermometer, and we want to see how we can translate the sensor reading to a discrete temperature that we can use then in the virtual state layer middleware of the distributed small space orchestration system. So basically we create an adaptation service, if you're familiar with the terminology of our system. In this slide you see the virtual state layer in green as usual, so there we see context data stored, and as you know, we have distributed nodes that manage the data, and each of them runs a knowledge agent shown in green here, and they store different data. And what we see here is that we have some physical phenomena, we have our sensor, then we have an adaptation service shown in yellow here, and then we produce some context. In our case we produce -10 degrees as the context. And in the dark green box you see how this one is represented in XML representation in the VSL. And as you know, the VSL forms a distributed knowledge graph, meaning that we can derive more information from it and infer, for instance, that it's winter or that it's sunny and so on. So we have distributed knowledge on the distributed nodes. In this tutorial we are not so much interested in the VSL but more in the process of getting the discrete readings of -10 degrees. So we want to look at how can we get from the physical phenomenon temperature to a discrete value, which is shown here in red. So the sensor measures something, we monitor it, we analyze it, and then we produce a knowledge context that it's -10 degrees. The cyber-physical system itself could be an Arduino Mega, so we use this setup and we connect the sensor acting as a voltage divider to the temperature dependent resistor, and we connect this to the Arduino Mega to the analog pin, and so we can measure a voltage that is proportional to the current resistance of the temperature dependent resistor KTY81 that we use here. So let's have a closer look how we can do this translation. So on this slide you see the sensor on the bottom left, and on top of it in the monitor component we see the resistance of the entity depending on the measured temperature, and in the analyze part we see the lookup table. So which resistance range matches to which temperature, and we are mainly interested in the part that was blinking right now, the -20 to 0 degrees. The reason is simply that we want to have a relatively simple automaton, so of course you could model many more ranges here. What we want to have in the end of our exercise is that we know that it's, for instance, -10 degrees, or that it's -20 degrees, or that it's 0 degrees. And for that we look at the automaton on the right. So here I modeled as a finite state machine, or also a label transition system, the process of going through the lookup table and determining which is the current discrete reading that we want to have as outcome from our cyber-physical system. On top you see the starting state, and from this starting state we basically have three possibilities. So either the measured resistance is below or equal 733 ohms, then we assume we are currently at -20 degrees. It's between 733 ohms and 802 ohms, then we assume that we're at -10 degrees. Or it's above or equal 802 ohms, then we assume that we're at 0 degrees at the moment. In our case, let's assume we're below or equal 733 ohms. So we take the transition to the left and we are in the state -20 degrees. Now let's assume the temperature is rising and we go above 733. So now the upper transition is taken and we arrive at the minus 10 degrees state. If the temperature would go below 698 ohms now, then we would assume that we're back to minus 20 degrees again. The reason for having this difference between 733 and 698 is simply a hysteresis. That means we do not want to jump fast between those states, we want to have a discrete value all the time. Now let's assume the temperature is rising more and we are going above 802 ohms. Then the next transition is taken on the right side now and we go to 0 degrees. And if the temperature would fall now again, in this case below 761 ohms resistance, then we would go back from the 0 degrees that we're just blinking to the minus 10 degrees in the middle, and so on. Okay, so this process discretizes and also quantizes, because we just have these steps between below 733, then 733 to 802, and above 802, which is a quantization. We will now model this automaton that I show here on the right inside the Uppaal tool. And what we will end up is what we see here on the right side. And let's have a look now how we create what I show you here on the right side in the Uppaal tool. Okay, so I open the Uppaal tool. Okay. And in the background we still see our label transition system that we want to end up with. Okay, so the tool opens and we already see a starting state. Okay, so maybe I just keep this model here in the background. Okay, and so what we want to do now is we want to create some new states. So I create our 3 states that we want to have here. And then the next thing you want to do is you want to add an edge, because we want to start here and we want to go somewhere. So I'll just add all the edges that we need, because I know them already. Okay, so these are the states that we want to transition in between. Can give them a name in a second. Okay, so looks similar to what we had. Okay, let's leave it like that. You see already that I did not model those yet, so I will tell you something about it in a second. Okay, so let's start. So we can just double click on the edge. Let's see. Okay, I have to move back to this tool. Okay, so we can click back on the edge, and so here we can enter different things. And so what we want to do is we want to add a guard, and in this case we want to say, okay, the resistance is below or equals 733. Okay, plus what we want to have is we want to have a synchronization for our test later. So this is why later we will have to put something in this synchronization field, and we'll say, okay, if we go this, then the temperature variable should be like minus 10. Okay. The next one here is the guard is again R is bigger than 733 and R is smaller than 802, and then we assume T is minus 10, so I did an error before. So here I wanted to say T is minus 20, of course. Okay, and finally here we say R is bigger or equal 802, so this is even wrong on the right slide, as we can see here. Okay, and then we say T is equal to 0 if we're there. Okay. Good, we can just move this, let's check. Okay. Okay, let's do this. Now we can read it a little better. Okay, so let's name our states here. So this is temp minus, or let's just name it minus 10, minus 20, minus 20. So here we could put also some invariants, but we don't need them right now. So they would be interesting for doing some model checking and verification. And here we do minus 0. Okay, good. Now let's do the same for the other states. Let's have a quick look what we want to put there. So here we want to put resistance is bigger than 733, and then we want to say T is minus 10. Okay, so you see a little bit that the layouting is not perfect, but well, it's not a problem. So maybe I should have also put the states a little further away from each other. Okay, then here the Guardian's resistance is lower than 698 ohms, and the temperature is then minus 20 again. And here we say resistance is bigger 802, and then the temperature is 0, and on the bottom, well, it does not want to take only the text low end. And in the bottom we say resistance is lower than 761, and then we say T is minus 10. Okay, good. So now we have that. And so now we need some more transitions, because this, we want to simulate it in a second, and this is a step-based simulation, and it wants to make a transition in every step. And so this is why for each state we have to add the identity, meaning, okay, if nothing changed, then just stay where you are. Okay, let's do that. And let's say if the resistance is smaller or equal to 733, then we do simply nothing. Okay, and if the resistance is, so I put the wrong one here, I moved it wrong, is between 733 and R is below 802, then we do just stay here. So this one is correct here. And if we are here, R is above 761, then we stay here. And so here I made also a mistake, because we want to stick between the transition points here. So we say if it's bigger or equal 698, so the hysteresis value, but the other one is correct. Okay, then it stays here. Okay, this should be correct now. Okay, and so now we have to define our variables. So this is, I should have done first, but basically it doesn't matter. So we say integer R is our resistance, and integer, so here we can also put a range, minus 20 to 0, but we don't have to for the temperature. So here we have the resistance, and here we have the temperature. Okay, good. Let's maybe rename this one. So this will be our analyzer, or let's label it CPS, because this is our cyber physical system. And now we want to test this one, and therefore we just create a tester. Let's see how that worked. I think it was file new system. No. So I need a new thing here. How can I do it? I can just insert template. Okay, this is it. Okay, and so now we just do the resistance change emulator. Okay, and so this will just change our resistance. And so let's see how we do that. Yeah, so we start in our starting state and add just another state. Let's see if it works like that. And so here we say, okay, we want to, okay, sorry, let's do it differently. So I'll remove the edge again, because we have to define some start state. So we start here, and then we do like this, and we call this one increase, and we call this one decrease. Okay, and so what we do now is we say, okay, we start here, and okay, we want to do some transitioning here, and we want to go from here to here, and we want to go back, and we want to go around here. Okay, so let's start, and let's say resistance is 700 at the beginning, and then here we say guard. We say once we are below, so the highest was 833, so we say once we are below this one, we say resistance is resistance plus 10. So we increase the resistance, plus well, I will tell you in a second. Okay, let's do it like that. Okay, if it's like that, then we just increase the, resistance. Then here we say if we are bigger or equal 900, then we say then we say just say nothing, we just stay where we are, it's okay with the value. So we just go here, and here we say we want to go back. Yeah, so here we say if we are bigger than 700, R is bigger 700, and then we say okay, R is R minus 10, so here we want to decrease. And if we are here, R is smaller or equal 700, then we want to go back to the decreasing again. And now let's see if we can test this. Okay, so we have initialization errors. Okay, so what is the problem? Unknown identifier T. Oh. Okay. Declaration point is not expected, so probably I just did wrong with this syntax. Let's just store it here. Uppaal CPS example. I think XML was a valid example. Okay, good. Let's go again to the simulator. I want to upload it, yes. The model contains errors. Let's check again. No such template, no such process. Okay. Okay, sorry for that. So I renamed it. So we have to rename this to CPS. Let's first test the resistance. Resistance change emulator. Okay. Okay, and now we see the global variables here, and then we can say here, okay, take always a random edge here, depending on the assumptions, and a random because it must not be a deterministic automaton. So I guess that at least. So it could have different transitions, and it's just choosing one. And so let's try if it's doing the correct stuff. Okay, we do the transition here. So here in the bottom you also see that it's doing the increase, and so once we go 900 it should move over, and now it goes down again. So let's just check if it goes correct to 700. Okay, we go back and then we go up again. Okay, seems to work. Let's stop that, and now we can do the following. We can link the two processes, and therefore I just name them process 1 and process 2 just for simplicity reasons now. So this is then CPS, and now we link the two. Okay, and to link them we have to use something that is called a channel, and we call the channel just O for linkage, and this channel means that variables are exchanged between the two systems. And so this one is the emitting process, because it's our simulator, and let's do that. Oh, so this is emitting to the other system whenever something changes. Oh. Okay, so I hope I didn't forget any of them, otherwise the system will complain in a second. And in our other system we want to receive this signal, so on each edge we have to put the O again. So normally you would do that immediately, I just didn't want to disturb you with the concept before, this is why I do it so late. Okay, again I try not to forget any, but we will see once we start the simulation. Okay. Should not forget to do it with the upper edges as well. So let's finish this side first. Okay, and do the last two edges. So those are important because the simulator will drive us, and so we could set the starting state to something here, and so it could also be higher. Okay, let's save it and let's see if the simulator is fine. Okay, there's two errors. Let's see what is the problem. No such process system declaration. Ah, yeah, okay. So I did this one wrong. So let's just call them P1 and P2. Save simulator. Upload, yes. Okay, looks generally good. So let's see. Okay, what happens? So I move this one up as well. And so what should happen now is that the simulator on the left does something, and the CPS on the right reacts to it. So, well, I don't like that they are called P1 and P2. So I would just call them emulator, call R emulator, and this one I call CPS. CPS and emulator. Okay. Good. Error. What is wrong again? Sorry for that. Duplicate CPS. Okay. CPS 1 or emulator 1. Okay. Okay. Good. Okay. Now I like it better because now it's clear what each system is. Okay, so here we see the time sequence diagram again. And let's start and let's see what happens. So these are the variables, and as I told you, so now the emulator on the left should do what it did before, and the system on the right should react to this emulation here. Let's see. Okay, so we're at -20, and once we go above, so now it's 33, we go up, so this is what happened now. And you see in each change here we also have a transition here. So this is an error I did at the beginning. I forgot this transition, so that it stays on the state as long as it's in the range. And okay, so we go up again. And so what we see is that our simulator is not going down enough, because the transition here is at 698. And I programmed the simulator that is starting at 700, and this one is going down when it's at 700, but it should more go down when it's at 600, because otherwise we cannot test everything. And so let's check and move it to 600, and also start, well, here we can start basically with whatever we want. So we can also start with 800, for instance. So let's test that. Let's go back to the simulator, upload it again. And so now we should see that it's also moving back to the left side again once it went to the right, and it should also, if we start with the 800 now, it should start with a -10 and then immediately move to the right. Let's see if that happens. Okay. So, well, actually I don't know why it didn't start here, but now the system should work correctly here. It should move back, and so once we go below 600, okay, now it goes back again, and this one should go down to 600 and then move up again. Okay, so now you have seen how to model the cyber-physical system that I showed you in the slide. So this one here on the left with the Uppaal system that we used here. Okay. Good, so I hope you enjoyed the tutorial and maybe give the tool a try. So this tool can do much more things. So it has also this simulator, it can do some verifications, so here you can add some invariants and you can check them. And this tool here on the right I didn't check yet, so it seems to be some traverser, some model traverser, so I don't know what it does exactly. Okay, yeah, so I hope you enjoyed the tutorial, and yeah, have a good time.